Chapter 11, Set A. Okay, 11. I'll get there. You just wait. So in Set A, so I'm on page 184. Look at figure 1, then fill in the blanks. So, geez. The figure 1 is all the way back on 181. Person B is blank and blank. Tall and chubby. So person D is tall. So look on page 181. Person B is tall, like 75 inches tall. That's pretty tall. That would be, what, 6'3"? And 430 pounds. While person D is short and skinny. How do you know D is skinny? Definitely short. Why short? Because he's very low. How do you know D is skinny and not average? That's not an option. Average is not an option. Okay, good. But looking at the graph on 181, how do you know D is skinny? It's lower than the regression line. The regression line represents the average people. Okay? Okay, look at figure 1, then say whether each is true or false. E is above average in weight. We're set A, 11A. So, is E above average in height? No, E is very short. So E is above average in height. But what about weight? I know. We're getting there. So is E above average in weight or below average in weight? What is the average weight? So look at the page before. What is the average weight? The Y bar is 180. So is E above average in weight or below average in weight? Slightly below. Okay? And the regression line at this point, some of you aren't paying attention, the regression line doesn't give you the average height and the average weight, but it does give you the average weight for that particular height. Does that make sense? So D is below average in height and below average in weight. But for all of the 62-inch people, D is pretty skinny. Do you see that? Below average for that column. E is below average in height and below average in weight, but when compared to all of the people that are 62 inches tall, that person is higher. Does that make sense? He's a little bit chubby for his height. Overall, he's below average in weight, but that's because he's short. Does that make sense? So the regression line gives the average weight for any individual height. So E is above average in weight for men of his height. True or false? True. So below average overall in weight, but for his height, he's above average because he's above the regression line. Okay, 3. A regression line is fitted to a small data set. For each subject, the table shows the actual value of y and the predicted value from the regression line. The value of x is not shown. Compute the prediction errors and the RMS error for the regression line. So here's what's happening. We have a football. Is this a positive correlation or a negative correlation? We have no idea, right? We're not sure if the football is shaped like this or any other way, and you draw the regression line, and then you create what is called the residual plot. okay, which eliminates the x's. We call this 0, and all we do is measure how high and how low, and those are used to create the root mean squared, which is essentially the standard deviation in two directions. Okay, so the actual values of y, I'm just going to take a picture of this. Oh, that's nice and fuzzy. So we would expect whatever x. I'm not having a good day. So we don't know what the x is, but with this particular x, we would expect 64, and the actual value is 57. So what is the error? -7. Right? The line, whatever, whether it's going up or down, we don't know. But this particular x value, we expected 64, but the actual point was down here at 57, which means we were 7 below the prediction. Well, your error for that value is -7. What is the error for the next value? +1. What's the error for the next value? +3, +1, and +4. Do we really care about positives and negatives? Oh, sorry. Oh, sorry. I'm so lost. There we go. -1 and +4. Do the positives and negatives really matter? No, because what am I going to do to them? I'm going to square them all. So what we have done is we have said the first one was 7 low, and then up 1, and then up 3, and then down 1, and then up 4. And then we're going to square all of those, add them all together, divide by 1, 2, 3, 4, 5, and then take the square root, and that will give us what is called the RMS error. Not yet. Okay. The RMS error tells us how we can expect to pick up 68% of the people. So 7 squared plus 1 squared plus 3 squared plus 1 squared plus 4 squared. Divide that by 5, and then take the square root. So that is 3.89. Okay. Oh, wait. So we need to multiply that by... Oh, they didn't... Sorry, that's the shortcut method. That's what you were talking about. So this says, if I take my football... No. I take my football, and I go up 3.8 and down 3.8, and I draw parallel lines, how much area is in here? 68%. Just like 1 SD. But finding that RMS this way is really complicated. So there's a shortcut to find the RMS error. The shortcut is you take 1 minus r squared and take the square root and then multiply that by the SDY. So this number right here, 0.389 or 3.89, that can either be calculated by calculating each error, squaring, adding, averaging, and then taking the square root, or the r value gives us an idea of how much everything is spread out. 1 minus r squared, take the square root, that times the SD of y will give us the RMS error. That's a good idea. We'll have to do that. Okay. Number 4, below are 3 scatter diagrams. The regression line has been drawn. A would be which error? So number 4, A would have to be 0.2, B would have to be 5, and C would have to be, oh, wait, scratch that. Look at the y-axis. So B is going to be 1. If you go up 1 and down 1, you will capture 2/3 of the graph. And then letter C looks to be more correlated, and the R value is actually higher, but the standard deviation is so much larger that it's going to be 5. 5. The regression line for predicting income has an RMS error of 2,000. It predicts somebody's income at 20,000. This is likely to be right, give or take a few $100s, a few $1,000s, $10,000 or $20,000, a few thousand. We would expect 2/3 of the people to be between 19,000 and 21,000. You understand that? Just like the SD rule. +1 SD and -1 SD captures 68%. +1 RMS and -1 RMS captures 68%. So we would say a couple $1,000s. An admissions officer is trying to choose between two methods of predicting first-year scores. One method had an RMS error of 12. The other had an RMS error of 7. Other things being equal, which should he choose? So what we have here is, we don't know what the graph looks like. So let's assume it's football shaped. Whether it's positive or negative, that doesn't matter. So we want to predict two methods of predicting first-year scores. So we're going to have some x value that is going to predict first-year scores. Okay? And one has an RMS error of plus, oh no, I hate it when that happens. So the first one has an RMS error of 7. So up 7 and down 7. And the second one has an RMS error of plus 12. So does it matter which one we pick? We don't know what we're using for X to predict. So maybe one is a GPA. Will GPA predict first-year scores? And the other one might be midterm test. Midterm test predicting GPA or predicting first-year scores. So let me read that again. One has an RMS error of 12, and the other has an RMS error of 7. All other things being equal, which should you choose and why? Did you guys look at the answer on this one? So if you go to chapter 11, section 1, which is on page, 63. It says the one with the smaller RMS error should be used as it will be more accurate overall. Does that make sense? So the first one has an RMS error of 7, which means 68% of the people will be within 7, up or down. And the other one has a 12. So the second method is less reliable than the first method. Yeah. So the R value for the first one will be larger than the R value of the second one. And you want to use the larger R value. So if the green bubble is the football for the first prediction, then this would be the football for the second prediction. So green might be GPA, and red might be ACT score. Does that make sense? So the GPA has an RMS of 7, and the ACT has an RMS of 12. Which one is a better predictor? GPA. Because it has a lower RMS error, which means it has a higher R value. Okay. A regression line for predicting scores has an RMS error of 8. About 68% of the time the predictions will be within 8 points, and 95% of the time the predictions will be within 16 points. The scatter diagram on the next page shows incomes for a sample of 168 working couples in Louisiana. Summary statistics are as follows. Husband's income with its SD, wife's income with the SD. If you predict wife's income at 28,000, ignoring husband's income, your RMS error would be, so if you're only looking at one value, if you predict wife's income at 28,000, ignoring husband's income, your RMS error will be the standard deviation, right? Okay. And then all predictions are on one of the lines in the diagram. Which one? What? All the predictions. Oh, yeah, the regression line. Yeah. Wow, that's a confusing question. Which of those three lines are we going to use to predict income? The regression line. That's a really silly question.